This is our first class, okay, and the class title is Data Structures and Algorithms in Python. My name is Jim Lai, and you can reach me at CSTUAI Google Groups. I think everyone should have already known that. So the class time is from 9:30 to 11 every Saturday, and at 7:30 p.m. to 9 p.m. every Wednesday. And today is the first one, and we have a little bit of special. So we're going to have a 2 hours meeting instead of 1.5 hour normally it will be. We are going to have a little break in the middle, so about around 9:30, 10:30, around 10:30, we probably have a 7 minutes break. So everybody can get a coffee, go to the restroom or something like that. So let's go to the next slide. So who is Jim Lai? Who am I? So I am an adjunct computer science professor at Foothill College. And I worked in the past as a principal software engineers in various cutting edge companies in the east side of the United States. So I've been here for about a couple of years, 7 years, moved to the West Coast. And I liked it here very much. Very nice weather. And I enjoyed, very, very pleasantly here. And you can imagine this in this season on the east side, it's big snow, big storms, everything like that. I have to shovel every day, so on and so forth. Okay, and I have a PhD in electrical and computer engineering. That's about me, and I have a little bit, some hobbies of myself. And if you want to chat with me later, and we can talk about that. So about the syllabus. So I hope everybody had a chance to take a look on the syllabus already. If not, please go over those and carefully and let me know if you have any questions. I would like to get this, lecture going in interactive ways as much as possible. Raise your questions anytime, interrupt me, and I that way, for anything. No, not the one to go to the bathrooms, but just anything about the class materials, anything about this algorithms, data structures related things. And the only reason you want to go to a class is that you have a live instructor there and you can ask questions and get the live response right away. Otherwise, you can, you don't have to come to here. You can go online and go to any one of those YouTubes. There's tremendous, wonderful learning materials there available, and go over those things yourself on your own pace. So if you want to come to here, take the advantage of this this time, this period of time, and to best use of the resources here available to you. That's the only real advice or true, honest advice that I can offer to you. Okay. Any questions so far?
Nope, not right now.
Not right now. Good. So we are on the same page. So textbook, okay, and this textbook is the one I selected, not really I selected, but I kind of inherited from the previous classes. And I think I found this one is really wonderful. It's complete. It's very comprehensive and covers tremendous materials. It may not be very good for the intro class. Now, for the people who first time get into this data structures, algorithms stuff. But you can have it as a reference. So anytime later you find something you not sure what is that, you can come back to refer to that textbook, and you can treat it as a dictionary or something like that, encyclopedia of data structures and algorithms, kind of like that. And there's a lot of Python examples. It's using Python as a computer language to present the ideas of data structures and algorithms. And it is a little bit expensive if you want to buy it, but you can find it online and a PDF file. It's free, and you can download that and put it onto your somewhere, and you can go online to read that offline. You can download the PDF file, so you will be able to read it. It's just not as convenient as a real paper textbook available on the desk whenever you want to read it. Okay, that's about a textbook. And the grading scale is going to be 15% for the participation, 50% of your weekly assignments. And assignments has two parts. Each assignment is, one is the homework, and the other one is a small project. Okay, and then we have 15% on the midterm, and then 20% for the final. And in the syllabus, we have listed the weekly schedule about the materials we're going to cover. It may vary, and I will kind of adjust that accordingly. It depends on everyone's need response, the majority of the class, to see how students would like the pace. You want to could be a little bit slower, you want to be a little bit faster, let me know, okay? It will take lots of your time, and to be really successful in this class, your hard working is the key. You have to spend many hours on this. It's not like it's not a movie. Come here and watch the movie and enjoy it, and it's done, right? So you have to put up a lot of hard working onto it yourself, and to really understand the materials, to build your computer science knowledge step by step, and so on and so forth. I haven't got an idea on who everyone's situation is and what your needs are. So I will go along, and then when I get the feedbacks, I can adjust myself accordingly. Okay, that's the plan basically. What's next? Let's see. So we have a homework and a project due every Saturday, and I will give you, today's Saturday, so I'm going to give you the first assignment, first homework and the first project, and it's going to be due the next Saturday, okay? And the next Saturday, I will give you the second homework and the project, and then they will be due the next Saturday. So, okay, and you have about a week to complete those work and submit them on time. I expect that to be on time. So if you have to submit late, you might want to give me a heads up. And if it really has some special circumstance, I might be able to waive the penalties, some points deductions or something like that. So, okay. Again, I don't want to scare you away, but you do need to spend many hours on it. If you find the things are interesting and fun, and then you are willing to spend time on it. It's just like games, right? People sometimes the computer science programming can be addicted to, and you willingly or unwillingly that without any noticing that the time just flying by, and you would have spent many hours on it and just try to get things right. Okay. So this is about rough introduction about what's going to happen in this next 7-8 weeks. So any other questions? I would like, actually, if you have any questions, ask me first. Otherwise, I'm going to ask you a few questions. Anyone want to contribute something? Okay, so first I would like to know if you could just put up on the chat. I could set up some poll, but I haven't done that yet. So I guess if you could just using your chat. Where's the chat session? Everyone see their chat? Let me see here. Where's the chatting?
Yes, we are chatting already.
Yeah, why I couldn't see that myself?
Click on that ... after more on the
yeah, okay. This interface is a little bit different. Okay, well, good. Okay. Yeah. Oh, textbook. Okay, somebody got the link for the textbook. Great. Thank you, Mike. So could you please let me know that people here that you have, and I assume everybody has some basic ideas, basic knowledge about the Python. Is this correct? Could everyone just say yes, or if he already knows something, and then if no, just let me know as well, so I will probably adjust accordingly. Yeah, great. Thank you, everyone, to let me know. And I assume that also. So, do you want me to cover certain, kind of some in the list, in the schedule, in the syllabus schedule that I have listed few chapters that I would like to. But still learning. Okay, I know but learning. Okay, and I'm going to, so let's assume this. I'm going to go over I'm going to change the plan a little bit. So I am going to talk about this algorithm things first. And then you let me know if, see if you want me to spend maybe a class on this next Wednesday, just talking about Python only, or some enhanced version of a Python, or not. In terms of the data structures and the algorithms, that we are not really focusing on the Python language. We are not. We are trying to build our knowledge on the data structures. and algorithms. The focusing is on algorithms. You can implement those algorithms in any languages. Okay, you can use the Python, you can use C++, Java, or any other computer science languages as well. So it's, if you have had already the basic idea, the basic programming skills of the Python, and that's good enough. Okay, you can devote lots of times just to study the Python. There's a lot of tricks and secrets or things that and you can learn the Python, which is a wonderful language. That, but that's not our focus. As long as you can use the Python and then and use the basic Python syntax, and then to construct a program that to write a code to do our data structures and the algorithms, and that would be fine. But if someone say, hey, I do want to go over something fun about the Python itself, and we can spend a class on that on the Wednesday. So at the end of the class, I probably will ask this question again and to get a poll to see how do you feel. Okay. So I'm glad that everyone does have some basic knowledge of the Python already. That's great to know. And also, anyone has already had some basic ideas about the data structures and algorithms? Say yes in the chat. Okay, I have a few, great. And that, no, okay. Maybe half and a half. So I will cover, so that looks like I need to cover the basic first, and then talk a little bit about advanced things, or mention that, and to leave up to you to do further study. That sounds like is a plan for me at this moment. Okay, thanks for everyone's response, and this is really wonderful. And let's just start. Okay, I am trying to cannot emphasize too much. Your feedback is really important to me and to yourself as well. Okay, and that way you can learn as much as possible from the class, and ask questions in the, you can raise the question, ask verbally here, or you can put up the question in the chat session as well. So if I see it, and I will respond it and adjust my presentations accordingly, okay? If I did not see it, and for some reason the chat window was covered by something else, please somehow raise your hand or something, let me know. And then I will address that. And if you have a question, most likely someone else in your peer would have the same questions as well. So please do you a favor and do your classmates a favor to ask. Okay. Okay, so far so good. And let me get to our normal things I would like to present about. Let's start the real stuff. Okay, before I go to the real algorithm things, let me bring up the my another PowerPoint slide. And Glenn, do you have anything to address to your students here?
No, just move on. I think it's pretty well.
Okay, okay, great. Okay, and interrupt me anytime if you have any questions, okay? Until too many students are asking the same questions, and I will do something then. Okay, let me see. How can I get back to my? This is being covered again. This one. Okay, everyone can see it?
Yes, we can see your slide.
The new slides, right?
Yes.
Okay, the new slides. Let me close that one, just blocks my view. And where's the chat? Where's the chat window? Huh? Where's the chat window? I need the chat window open there. Oh, chat is here. Okay. Oh, okay, good question. And the other PowerPoint is not shared with us yet. Correct. And I think this class has been recorded. Is this correct, Glenn?
Yes, we see the recording on the upper left corner.
Okay, so if the class is being recorded, so I think you can come back to view the slides in the recording. And I plan not to put the further slides back up there in the shared drive. That's my plan at this moment. Okay, so let's put a weight on here. Are you seeing the PowerPoints only, or are you seeing the chat window as well?
We see the PowerPoint only.
Oh, okay, you don't see the chat windows here. Okay,
No.
Okay, great. Thanks for letting me know. So I put it up here, so just so I know any questions come up or not. Okay, so here goes to our main topic, the algorithms. So what is an algorithm? Okay, algorithm, you can Google it and you can do online search or something like that. Basically, a simple graph here is that you have whatever something, a bunch of data to input, and this algorithm will cranking on those input data and produce something nicely you want. Okay, and it's basically kind of like you can think about a machine, a plan. It just produce something according your pre-designed ways to get something you want. And of course, some algorithms are better than the others to achieve the same results. Okay, and Google Maps, is you can think about that. It's something you have a request. The Google Maps have an algorithm in it to produce what's that? A plan for you to drive from A to B, right? It's as simple as that. You can if you plan. Another way is a chess, right? A chess game that you play against a machine that the machine has an algorithm built inside, which, whatever your input is that, and he can, the machine will act accordingly, and according to the algorithms built inside to do his part. And so what's good? What's the anyone can think about any other things about algorithms? Whenever you heard the word algorithms, you can put up in the chat if you can. So what is the most important part of the algorithm? What do we ask the algorithm to do, and what really matters to you about algorithm itself? Anyone can say something?
Complexity.
Complexity, yeah. How complicated this algorithm is. If it's very complicated, and actually the human being, I have some algorithms kind of built into my mind, and you play the chess with someone else, it's just intuitively some kind of algorithms. It's a plan, or maybe it's a roughly plan. It's not, and the plan changes by itself dynamically. It's not preset, right? So it's kind of complicated. You can think about this as complicated. I was playing chess with against my wife the other day, and she said that you are using algorithms, against me, and why? So that's why I always lose. So she was complaining about that. So I said, this is this is human beings are more complicated than the algorithms, but it's sometimes, a lot of times, you're gonna lose to the algorithms pre-designed by the machine. Actually, the machine's algorithm is built by men too, right? By people. So the complicated one, if it's too complicated, it doesn't matter if the computer can do it. I guess yes, right? The computer right now is very, very powerful. They can do lots of things. Human beings have to think spend many hours to think of the computer, probably take a second to complete. So the complexity is one thing. For human being, that's why we build machines to do the algorithms. And complexity is something that we need to talk about it. And this is actually to the point of the next hour or so. We're talking about complexity about an algorithm. But again, and then what is the most important things about algorithms? What do you ask the algorithm to do? You want to achieve something that you want, right? And you want it to be, the results to be what? Correct or wrong? You want the correct result, right? And you want the correct results in a timely fashion. Think back about the Google map, right? If the algorithm is built in there, I want to go to here from my house to Glenn's house, right? So if the algorithm doesn't work, it leads me to someone else. So that's not going to be good, right? And also it needs to be done, somehow in a manageable time frame. Now I wanted to, get out. Let me know how can I drive this, and it has to be provide the results back to me in a reasonably, in a few seconds or a few minutes, right? If it takes an hour, it takes a day to calculate the algorithm, it's too late, right? So we want the algorithm to be correct and to generate correct results, and we want the algorithm to calculate the results in a timely fashion. So that's back to the complexity, right? Some algorithm can do this, it builds, so it will spend little time to generate results for you, but other algorithms might be, very slow, and because the algorithm designer doesn't have does not understanding the problem completely, and build an inefficient algorithms. So we want an algorithm to be efficient. Okay. So we spent a few minutes about this algorithm in general, and then let's see what kind of algorithms are good, what kind of algorithms are not so good, and how do we measure the complexity of an algorithm. Okay, we want to know what's going to happen. So this slide shows us about the run time. So we want the algorithm to get the correct results in a timely fashion. But this algorithm, this picture shows here is that the algorithm time based on, it is actually, if I calculate it from here, from my house to Glenn's house, it takes like a second. But if I want to calculate the results from here to, maybe I want to go to South Africa for whatever the reason. So it will take longer time to generate results, right? So it really depends on your distance. So this algorithms in general, if the data give you certain data size is small, the time it will be small too. If the data is large, when the data grows larger, and the time spent to get the results will be larger as well, right? This is intuitively true, and so people will say, let's see how this algorithm, good or bad. How do you measure it, right? So in this example here, look at the picture. Let me put up my annotation here so I would have a little. Okay. Okay. So here is a graph, this picture. It's basically showing that when you measure this time, and it depends on, but it's even the same algorithm, same data, it might be sometimes when you measure it, you will get some. Where's my? I just lost my cursor. I'm sorry. Technical difficulties. I lost my cursor, and why I can't move my.
One of the way you can unshare, and then temporary unshare and reshare again, and see if we can see your cursor again. Do you see the Zoom's sharing options? You can stop sharing on that red button and that red kind of say rectangle bar. Click on that and share first and see if you got your cursor again, and then you can reshare.
Did you see my slides went away?
No, your slide is showing on, maybe there's a lag. But currently we still see your running time, that slide.
Yeah.
Maybe you have to wait a little bit of more time. Did you stop sharing now, please? Just give it a try.
Let me try this. New. Oh yeah, it sounds like it's already you are sharing. Stop sharing here. Right. Oh, the cursors.
All right, you are flipping. Now we see your first slide.
Yeah, you see my flipping, but I couldn't get the stop sharing. Couldn't move my cursor to the stop sharing part. Okay. Let me see here. Okay, I got a few questions. A few people ask me about sharing the slides, to upload the slides. Yes, I can consider that. And most of the things, those slides are in the class, in the book materials. They are pretty much taken from the books. It's not a big deal, I guess. I still want to get back my cursor. I can kind of moving my.
There's another way to stop sharing is using the hard key. For Mac, it's a Command Shift S. You want to try? Are you using Windows or Mac?
I'm using Macs.
Okay, Command. Press Command Shift S.
S.
Yeah, single or simple. Yeah, now you are stop sharing. Your sharing is gone. Did you find your cursor?
Yeah. Now I have my cursor now. So
okay.
I'm back again. Yes, thank you.
Sure.
Thank you for the help. And let me share the screen again. And okay, now I have the cursor. Yeah,
we also see your cursor moving around.
You also see my cursor moving around. I was put up a new annotation. That's where something got stopped here. Okay, let me see here. Right, so you can see my annotation.
Yeah, I see the red arrow. Yes.
Yeah. Okay, so here's the point. So if the algorithm runs and sometimes it takes little time, sometimes takes longer time. Okay, and the average is here for the data of 1,000. When the data moves up to 400 samples, and then the best time you run this algorithm is 40, and the worst case is that you run multiple times. So sometimes small, sometimes larger. This is the larger one. This is the worst case, and this is the best case, right? For the same data type. So you have an average. So this basically the picture just showing you that way. So which one is the most important one around this worst, average, and the best you would like to know? Any idea? Where's the chat room? Can someone just say something? What do you think? And the chat, you can chat to, you can send a message to me or to everyone. That's up to you. You can select the sender part.
I have a question.
Sure.
You mentioned about that the same algorithm, if you run it many times, you get a number. My question is, for the same algorithm, if you're running many times, I do see that one might be varied, and why the time is varied.
Okay, good question. So the same algorithm run the same data. It might be it might varies, right?
Yeah.
Yeah. So I actually meant to be that the data that you input. So let's say example here, right? There's this 400 with, oh, not again, no.
Yeah.
The cursor is gone again. I think somehow to do with this
Yeah.
this annotation things. I'm sorry. I have to go back. Command shift
Command.
S.
Yes.
Okay.
Now you stop sharing.
Yeah, I guess I'm not going to use the annotation again. So
Yeah. Yeah. May not be. Sure.
it's not a good idea. Let's go back here. Okay. So I just used the mouse. So little mouse here. So
Yeah.
okay. So we have, let's say we have this 400. Oh no.
Yeah.
We have this 400 of data, but the data might be, even though the size of the data is 400, the contents of those data might be different. Okay. So example of this is that, how can I think about example? The data size is 400, but this 400 data might be, oh, shoot. And it might be all empty data, okay? And there's a, you think about something like, how can I get an example? So you have the 400 size data, and the data might be, let's say it's randomly from 0 to 100 or something like that. And your algorithm will calculate the something based on the data, okay? So if it's 100, and the algorithm will do something fun to reward you something, or no, it will do some kind of weird things to let's say generate firework. I'm just randomly pick up something, and if it's 100, I generate big fireworks. If it's a 0, and then I do nothing. So, and when you generate the fireworks, you have to do a lot of things to generate the fireworks. So even if the 4,000 data set, if it's all 0, you probably do little things, right? And that's the same algorithm runs, and they say, oh, it's all 0, so I don't do too much work. And that's where the best case comes in. But if it's all 100 in the 4,000 of data, you have to do lots of work. So you have to spend a lot of time to do that. And in the running time case, it is the worst case.
Okay, because I noticed that the two things. One is when we do this like leader code, have about 50 some test case. Each time it will run quite a lot. There's one thing. The second one if I do the coding profile and running the time it, for example, and typically the suggestion is run 1 million cycle, essentially 1 million times to get an average number. If I'm run like 10 times, I see that the time vary quite a lot. It's same data set. Essentially, the data is the same, just the running differently. And in the time-it profile case, actually, I'm running my own PC. I was wondering, is there something else might be interfered with inside the computer? Some other programs running or maybe differently. So the machine might be located assets differently in a different time.
Yeah, that's very possible. That has to be case by case study. So I'm not sure if everyone else got his question. It's basically saying, just, in his experiment or something, just everything seems to be the same, but somehow it still varies. So she's wondering about if the computer is doing something else, if that's possible. Yes, that could be possible. It varies. But here we are talking about, it's basically, the worst case is most likely is the data contents driven. What kind of data set? So that's why the data here becomes a commodity. So what kind of data do you have? You have how many valuable data, how many valid data you possess. That give you, will test your algorithms more meaningful. If you just have the same kind of useless data, it's not going to efficiently check your algorithms. Okay, that's a very good point. Okay, thank you for asking. So go over here. This in the most. I just read over this slides. If I think most of them probably have already read it. So most algorithms transform input objects into output objects. That's obvious, right? The running time of algorithm typically grows with the input size. That's also obvious. So average case time is often difficult to determine. It's just average, and you don't know how much time that's going to spend. And I was asking the question when I got the arrow, when I got the mouse key, the cursor frozen, was that which one do you think is most important? The best case? Oh, why keep doing this? The best case, the average case, or the worst case? And anyone bother to just say something? What do you matters to you? The best case, the average case, or the worst case in the chat room?
Typically, we only consider worst case. That's a bottleneck.
Okay, good. Yeah, so it's the worst case. Yes, definitely. You want to have something to have a guarantee. So like here, like I am asking the question and I'm waiting for you to respond. And sometimes I get, people answer the question right away. And that's the best case, right? It's a 0-second delay. And sometimes they may take, a few seconds, and some people might just take maybe even a minute to get me the answer back to me. So I probably will not wait for a minute to for someone to get the questions, to get answers back to me. So I will set up myself worst scenario of maybe 5 seconds, and then I'm just going to go to the next slides or something. So the worst part, the worst case is the one that you want to have it considered in your algorithm design, right? So that's there's a lot of examples about this worst case. Anyone bother to share any ideas of what do you think? There's any other cases that worst cases is more important? I'll give you another example, right? So that's in a similar one is that you have long distance international calls or something like that. You have this delay in the conversations. So you say something, the other people coming back to you, and if the delay is too long, the conversation is going to be very hectic, and you cannot carry a real-time conversation. So the worst case of delay that built into the system is more important, right? Is the tolerable. In a financial stock market transaction that you put an order there, you want that to be executed within certain amount of time. You cannot just wait for, an hour later. That's imaginable, right? Unimaginable. Okay. So we are pretty much interested on the worst case. So one is that in an algorithm case that it's easy to analyze and it's crucial to applications. Okay, so it's the worst case that you have to consider. If you get better results, great, why not, right? But as long as you can bound it within certain amount of time and that kind of is acceptable, then your algorithm is good. So you're all set, right? And you're hoping for the best, but the worst is kind of a guarantee. And so that's the way that we want to consider. How are we doing in terms of time and the speed of the class? I think we are getting a little bit slower than I thought. I would rather to be a little bit faster. Anyone want to be faster or slower? Let me know in the chat window. Okay. So how do you measure the time? Okay. How do you measure the delay? You can run some experiments, right? You can write a program and implement the algorithm, and then you just run it. Okay. Here is a piece of code here. Oh. Here I was going to use the notation, but it kept my cursor frozen a couple of times. I was afraid to use it again. So you can kind of see my mouse here. So this is a piece of code. This is a Python code, and I assume everybody can read it, right? It's using the time function, but the time function is not part of the standard Python environment. So you have import the time from the time modular. And then you usually say, let's record the time. Start time is this. You run your algorithm and you record the end time and by the function called time. And then you calculate elapsed time between the end time minus the start time. And this piece of code is simple, but that's the way you can use, and you can put up whatever the code here, run algorithm part of your code where you want to measure the time. How long does this algorithm takes to complete? And you put a timestamp before that, you put the timestamp after that, and you minus the end and the start, and you get this time. So if you put up you recorded those elapsed time and you put into a graph, and you will see here, this is similar like the one that we have seen before. Depends on the data set here from 0 to 100. And you might have sometimes the best case, in this case, in the large data set here. Any other question?
So you have 3 dots because you executed it 3 times?
No, not 3 times. It's actually, this is the 3 dots is you do this many times, okay? And then you find the fastest one is here. So it takes maybe, let's say this is around 750 or 750-ish. I'm sorry, 7,000, 750, 7,500, right? 7,500, 7,500, 7,500 milliseconds. So it's basically, it's a 7.5 seconds, 7.5 seconds. This is the, where's my cursor? I'm scared about my cursor now. So this is the, so you find all those results. The best time is 7.5 seconds. Sometimes take a longer, some take a shorter, but the fastest one is here. And then the longest one is maybe 8.5 seconds. So, and this is average is the middle one. So worst, best, and average. Those are 3 dots. And you can see this again, this is illustrate that when the data set's going up and your execution time goes up as well. And the worst case is going up, the best case is going up, the average is going up as well. Make sense? Any more questions? So this is one way to measure your algorithm. Say, hey, is this good or is this bad? And am I going to tolerate this? Is 9 seconds okay for this particular case? Am I able? Is the client, is the user willing to accept 9 seconds execution time for a data set of like 100 or something? Okay. So this is one way to do it. This experiment way is that you have to run many times of the data, and it's and there are some limitations here. So this is so if you want to compare two algorithms and to see which one is better, you have to have the same hardware and the same software environments to do so, and also to run this takes many you have to be time consuming, and also you have to implement algorithm, of course, first. And sometimes you have an idea and you don't have to write a code right away before even to see if this is feasible or this is not. You don't have to do, if there's a better way, we would rather not implement algorithms and write a code to do the experiment to find out if this algorithm is working or not. So we are thinking about a better way, thinking about maybe it depends on also depends on the problem itself, that if we can find more how do I use the word, that not that hard working ways, kind of a little bit of clever ways, more efficient way to calculate, to know the complexity of specific algorithm. Okay, that's what I'm trying to get to. Okay,
may I ask another question?
Sure, shoot.
So we're talking about this algorithm speed is very interesting. So if we have a same algorithm, we loading multiple users simultaneously, that's called a loading test. And we found actually that when you're loading to certain limits, then this actually the time consumed is much more. What's the reason for that kind of data interpretation? I did a test. For example, the algorithm might have in the beginning is a flat. If you're loading one more user, is like a flat. But when reaching certain time, certain kind of number, then increase exponentially or something. What's the reason for that increase?
That's good questions. I don't know, simply. So we have to study the case, and we need to know much more than a theoretically assumption that this is because of this, because of that. It could be many reasons behind it. And we could discuss about this in further to your specific experiment or to your specific case. But I like all the every questions. Although I don't have the answers to some of the questions, but at least give everybody a food to eat, to think. Okay, so that's great. Thank you. And what's your name? I'm sorry.
Charles.
Charles. Okay. Thanks, Charles. So now this course I am intended to, and I'm trying to, and I hope it will be more interactive, and it's more discussion ways, and ask any questions, no matter how simple it is. There's no stupid questions. Okay, here, period. So, and so that way you learn something, and I am contributing something, and everybody is happy. Okay. Okay. I think I have to go fast a little bit. What's the time right now?
10:37.
10:37. I said that it's going to be a 5 minutes break around the middle. So let me, I think I just, it's way slower than I thought. So I am going to go into the next section. Let's have a break. Everybody wants a break?
5 minutes break, please.
Yeah, 5 minutes break, and you can think about what are we doing so far, and let me know in the chat rooms. And although I'm trying to be fast, but it looks like my tendency is getting slower. I just want to sometimes talk too much things that I think maybe it's very obvious. So let me know your feedback. Thank you. We will be back in 10:38 right now, and so 5 minutes is 10:43, 10:45. Okay, so 10:45, a quarter to 11. That will be back here, and we have 2 hours today. So
Okay.
thank you. Feedback is most of the people want to be a little bit faster or even double the speed. So let's try that. And if you have questions, let me know. Okay. So instead of doing the, everybody's back, right? Can you say something here in the section?
Yes, we're back.
Okay.
We're ready to go.
Okay. So instead of using the experiment kind of a time-consuming way, and there's another way we call it theoretical analysis. And we want to build a function and try to characterize the algorithms as a function of input size m. Okay, so if the input size is getting larger, how my the running time goes up with it, and how does it look like? Okay, and again, this m data has to take all the possible input data. You don't want to have the input size just increase by itself with all zeros in it, and it doesn't. You have to be all possible kind of the input data. So the theoretical way is that somehow, and then in this case, you don't have to implement, even though I'm sorry, you even don't have to implement algorithm anymore. You just write down your algorithm. What do you want the algorithm to do in a sort of a high-level description language or a way? We call it pseudocode. I think most of the people must have heard about that in the pseudocode. It's just you don't have to write the actual code. It's just theoretically how this code is supposed to work, and from the exam on the paper, and you can sort of to see how this algorithms, the complexity of the algorithm in terms of the m, how the time goes when it's get executed. Okay, so the pseudocode, it looks like very much like English, and it's very, here I need to point it out, is something like actually very like a Python code too, and so that's also a easy way to learn Python versus the C++ and Java. Anybody else here that actually they probably is a programmer of C++ or Java? Anyone? say yes in the chat room? So okay, so and so here is some kind of a pseudo code looks like. If then this is exact in terms if then else, it's kind of a standard way. While do, this is it's a variation of a Python, kind of like that. So you can if you have already known Python, you probably know all those meaning. This is just basically English meaning. It's just the structure has to be a little bit structured. Okay, and each one of those kind of basic things will be counted when they are put on the paper. We say this is the each one of them may be taking a machine cycle to run the code, which you can calculate all those running time and then add them up, and this is all the time that you're going to spend for this piece of a code. Okay, so here is just some of the basic pseudocode looks like. When we get to it, and we can describe more. And here is there's an assumption here. Okay, so it looks like it's we have unlimited, here notes, it's unlimited memory things that you can store your data. So the memory size is not an issue here in this RAM model, random access machine model. So everybody can your code can access unlimited number of memory size. This is we are just talking about the running time of your code. It's not considering that how much space that your code is going to take, and that would be another complexity about your algorithm, and it's not in the picture of this discussion. So there are certain things that are important that basically if you kind of like this is a typical functions that look like when your data set n goes up and your runtime goes up, in what fashion? In a constant fashion, in a linear fashion, in a quadratic fashion, or whatever, or exponential fashion. So there are 7 different typical functions look like, and your specific algorithms may be one of them, may be something more complicated than these ones, and maybe the combinations of those ones, and which one will be the dominant one. And this is something that we can talk about it. And in the homework, there is one that you're going to fill up a table, and which is relevant to these functions when the data set's going up and the execution times goes up, and you are trying to measure how much the time will be expended. But the homework is put it in a reverse way. It's limiting the amount of time and see how many things can be done. It's the same idea, but it's in a reverse fashion. So you will see that table in your homework to do that. Interesting here, I want to point it out is that this scale is not a linear scale. It's a log scale. So, okay. So whenever it's in the log scale, and then this linear function, a quadratic function, a cubic function, they are all appearing as a straight line, and it's in a different slope. And the slope, if the slope is 1, that's linear. If the slope is 2, that's quadratic. And if slope is 3, that's cubic. okay? And you can study to see why this log scale make things look like straight lines. There's some simple math involved that you can find out yourself. If in the normal scale, what it looks like is this. If it's a constant, means that whenever data goes up, the data set goes up, the time you spent is constant. It never changes. It doesn't have to change. It's just like straight lines, okay? And if it's a linear, that's the one here. And it goes up and this goes up in a linear fashion. The larger data, the more time you spend. It's a linear fashion. If it's a n square, it's a quadratic go. When the data goes up, the time spent more dramatically in n2 fashion. And this is the one you want to avoid. When the data goes up, it goes up exponentially in the power of n. And this is no good. This algorithm, so it probably can do certain things within certain data set, but if the data size gets larger and this algorithm doesn't bound you very well, okay? So how do we calculate the primitive, how do we calculate, you know, in a theoretical way to see how much time that is spent on it? We assign certain primitive operations and as a constant unit, like evaluating an expression, accessing a value to a variable, so x equal to 3, that counts one operation, right? And the x plus y is another expression that, you know, it counted as a one operation. So, and indexing to an array, like if you want to if you have array A, I want to take the fifth element of the A, so A square phi, and that counts one operation, and so on and so forth. So each one of those counts as one operation. And then we can see there is a simple program here called find max. Everyone with me, that the speed is okay? You may not be able to read every line of the slides, but I guess you don't have to. If you really want to, you can come back and in the show or in the slides, see if I decided to put the slides in the shared drive and you can access there, okay? And you can read the manuals, you can read the books, okay? We could do the book, and the book has everything in it. And here is that I'm trying to explain certain things. I think it's the most important ones and answer your questions. So here is a code, piece of code, a Python code. It defines a find max function. There is arguments called data. This data is a list. The list means a couple of data in it, just not one single data, okay, or a single of elements. In this case, is a integer of a list of integers, okay? So if I give everybody a moment to read this one and see if anybody, then we can analyze this piece of code, see how much operations this code executes. So this code is basically want to find the maximum number in the data set, data list. Data list might be 10. One of the example is that something, if you can't kind of see the code, you can always assume, say, I have a data. The data is only 1, 2, 3 in it. The first one is 1, the second one is 2, the third one is 3, and so on and so forth. And then try to walk through the code yourself and to see if that makes sense, and then extend it to the size of n from 3. So that way you might have a little bit of simple entrance to get the point. Okay, so here it is. The data comes in, and they initially say, I don't know what the biggest data in this data set. I just assume this is data 0, and I just set it to be the largest one. And then from this data, and I take every one out of the data and to check to see if the data, this value, is larger than the biggest one. If it is, if this is true, oh, this is not actual Python code, right? So, oh, yes, it is. Oh, that's missing. It's a Python code. It's missing quote here. I'm missing the column here, right? If something, you have to have a colon, and then what's of the next one? Yeah, that's missing something. It's not a pseudocode. So this is a three quotations. That's typical Python syntax for the comments. Okay, so if the value is larger than the biggest one, I record that the current value one to be the biggest one. And whenever go from 0 to 1, 2, 3, finish all of them, and then I will find largest one and return the big one, the biggest one. So in this code, and you have the step 1, step 2, step 3, step 4, and so on and so forth. Step 1 takes the 2 operations, and step 2 doesn't take any operations because it's not a Python code, it's just comment, right? The number 3 takes 2 operations because the index takes 1, and the assignment takes another 1. So you have 2 operations, and so on and so forth. So remember here, the number 4, it says it takes 2 n operations. Why n? Because you don't know how big the data size is. It's n size. If the data size is n, you take the data 1 out of it. Each time is 1. You take n of the data. Each time you take 1, take 2, take 3, take 4. And when it's complete, it will take n of those operations, right? And each one of them is going to be assigned to the value. So you have additional n operations. That's where you have 2n operations. So you keep listing every one of those operations to see how many operations it costs you to do this. Look at the number 6. The number 6, you think this assignment is 1 operation, right? Why it says 0 to n? Because there's if statements here, number 5. So number 6, the line 6 does not get executed, depends on the line 5. So here there's the best case and worst case scenario here. So if none of them value in data, or if the number 5, line 5, never being true, the value is always smaller than the biggest one. So the line 6 will never get executed. So the best case is you don't take any operations, you take 0 operations, right? But if every step, the value accumulated from the data is always greater than the biggest one, the current biggest one, then this biggest one has to be updated every single step. That takes n operations. So this is 0 to n operations on line 6. That's sometimes we talk about this worst case and the best case, and depends on your data set, right? Make sense?
I have a question. Why in step 5 we have 2n? What are 2 operations?
Oh, okay. And 2 operations, the comparison value, the value larger than biggest is 1 operation, right? And then it depends the operation. If it will jump, it will cost you another line of code to do the next. So that's basically the next operation. Instead of n comes from the number 4 because the 4 goes n times. So the line 5 will go n times. But the n times is 2n is just simply because you have two operations here. One is the comparison, one is the if the comparison results, depends the comparison results, it will jump into different locations.
Okay, okay. One is comparison, while other is decision after comparison.
Yeah.
Okay, cool. Thank you.
And here is something that we want to know why they are doing this, but it's just give you a confidence that something later you know all these two operations are irrelevant. We don't have to know all those things. But in order to know they are not really important, we have to know why they are not important. So that's why you need to know why you have 2 here, why you have 1 here, why you have so on and so forth here. That's kind of a tricky, right? So the point here is that you want to know this line 6. Sometimes it's 0 operations, sometimes it's n operations, and that contributes to the worst case and to the best cases. Okay, good questions. And sometimes I was wondering about too, why here, why there, but it's just something in order to know that they are trivial, they are not important, and then you need to know why they are trivial. It's kind of something contradictory to yourself, right? Okay, so based on those, you add them up, and this algorithm, this function, this function is called a find max function, executes phi n plus phi primitive operations. Okay, that's in the worst case. It's a phi n plus n. The best case is 4n plus n because one of the operation is from 0. One is the 0n, one is the 1n. So that's the difference. That's n difference between these two. So then, so the actual time is this, whatever the time execution, the time actual, oh, sorry. So the actual, this is not the, so if the t, let's say this t, the total time is the worst case time, and then we will see that it's definitely going to be less than the phi n plus n, but it's going to be larger than the 4n plus phi. That's all we know so far. So for this algorithm, it's bounded by 2 linear functions. One is phi n plus phi, one is 4n plus phi. And in the end, you will know this is, this plus phi or minus phi, or no minus phi, okay? Plus phi plus some constant, and the factor of the function, the 4n or phi n doesn't not really matter because we want to know why it does not matter. We all know this function is linear bounded complexity for this particular find max algorithm. Okay.
So we assume that each operation takes the same time, yes?
Correct. It takes the constant amount of time. It doesn't matter. It's actual. It does or it does not, as long as it's constant. Sometimes maybe the index operation takes quicker, and the assignment operation may take longer, but as long as they are constant, that's the key here. It doesn't grow with the size of the n itself. That's the key. And we are assuming that one takes 1 second, the other one takes 5 seconds, but it always takes 5 seconds. It's not, the 5 seconds doesn't grow because the n, when n goes up, you still take 5 seconds for each operation. That's the important thing you want to know. Although the total time, of course, goes up. 100 times, you will 100 times times 5 seconds, right? But each time, as long as it's constant, and all those constant time, you will find later that they are not really important to us. Okay, so now we want to find out how this grows. When the n goes up, how this time spent on it goes up. How does it look like? That's something we want to know. And that's more important because especially in this internet world, the size of the data goes up and how our algorithm can comprehend those data and in what fashion. Okay, so here is some kind of typical growth rate looks like. We have the runtime. The one that we have is somewhere around the algorithm find the max is the Cn one. C is a constant here. Okay, everything the C is just stands for constant. It's a factor. It's maybe 3 times faster or 5 times faster. 5 times faster, of course, is oh, I'm sorry. The n goes up, so this way goes up, and then it always times the 5 versus 3. The 5 sounds like worse than the 3, but you will find out, later on, they are actually they are all bounded by the n. So it's the factor is not that great important. But here is just gives you a table for all this typical 1, 2, 3, 4, 5, 6. That should be another one. 7. Oh, there's a maybe constant is another one. 6 ones, and then we have a homework that looks like similar like this one, and ask you to calculate how many things you can get it done within a certain time frame, a different time frame. In a second, in a minute, in a year, in 100 years, how many things you can get it done, okay? So be kind of prepared. The example here is that you see if our runtime is constant times n squared, means that if the n goes to increased by 1, so n becomes n plus 1, how our execution time goes up. What it looks like, you just replace the n here. Oh, I need to use the notation because that way, but the notation gets my cursor frozen, so that's bad. So you replace this n by n plus 1 and do simple mathematics way to expand it. You got something like this. It's similar to this way in terms of the growth rate. But if the data goes up a double size from n to 2n, this is something you will be. So if the n plug by 2n, you got 2n, then 2 to the power of square. 2 square is a 4. So it's going to 4cn squared. So this basically means if your data goes up by double 2, but your total time is going to 4 times larger than your original time. It's quite joyful when the problem size doubles. And for the other things goes up too. So this is something exponentially goes up.
Can I ask,
Yeah.
what would a code look like when the running time is proportional to log of n?
Okay, good questions. And I give you a simple example is that if you do something, search algorithms, if you cut something into half, and then doing that, that's going to be the log. So I give you an example is that that's a little bit far ahead, but I think it's interesting. Let's see, if I want you to guess a number from 1 to 100, and I can start guessing from, is this 1? No. If it is 2, if it is 3, if it is 4, eventually you will get a number between the one in my mind. What is the number, right? So that's called linear searching.
Mm-hmm.
The other one is that I say, hey, is this 50? You can ask me, is this 50? Is it larger than 50 or smaller than 50? I say, yes, it's larger than 50. And then you cut the rest of the from 1 to 50 out of your mind. You think, oh yeah, and now the rest is 50 to 100. I only need to ask you the second question. And is this between, is this below 75 or it's above 75?
Okay.
And doing that fashion, your algorithm is much faster in a log. Oh, sorry, my power line. Okay, we'll see all those interesting algorithms later on. So, if you put everything into the graph, when the size goes up, and how the time goes up, and that's very interesting to plot. And one of the charts that if you can run your data set, you have something you can get everything is plateau, and then it suddenly goes up, depends the size. If you can get some data like this and draw the picture there, and we both can analyze it, and that would be something fun. So in this case, here we have the red line and we have the blue line. Oh yeah, there's a two sorting algorithm. One is called insertion sort, that's the blue line, and the merge sort is the red line. When the data set is smaller, looks like the red line is above the green line, the blue line. I'm colorblind, it looks like. Then it takes much more time to complete the sort. But when the data set goes up, and you will see the merge sort is much better. It executes much faster than the insertion sort. So you are not only see, hey, if your data set is always less than 100 for somehow that you can limit yourself with that data set, you may want to choose the insertion sort. But when the data set goes up, you don't want the insertion sort, right? That's going, and this looks like the n square going up tremendously. And this is here an example of that specific numbers for the calculation. Make sense? Okay, so here is something we're going to talk about why the growth rate is not affected by the constant factors or the lower order terms. Remember that we had earlier that our earlier example, find the max is 5n plus 5. The 5n plus 5 only matters this the n, and plus 5 does not matter, and the factor of 5 does not matter. Why? Because we can see here that we have two examples, and one of them is the linear one. It's a 10 squared. It's a really big factor. It's 100. 100 times n plus 10 to the power of 5. That's what? That's 100,000, right? So really big numbers. Are those big numbers matters? When the n is small, it does matter. But when the n goes up really, really big, this line is this line. Is this dotted green line is this line. And this line is the n line. When the data goes really up, the trend, they are all they are in parallel. They are all the same, right? When the data goes really, really large, and those two lines are kind of getting closer and closer, asymptotically, they are kind of merged to the same line. So that's when the data set's going really, really large, and then only the matter of this n matters. Similarly, for this quadratic function, this specific function looks like it's this line, the dotted red line, and this is the n square line. When the data goes really large size, and these two are going to approach to the same place. Okay, Where's my time?
It's 11:18 right now.
11:18. So I think we are. This is doing much slower than I was imagined. So let me see if we can finish something for this one, and then and I review this a little bit on Wednesday, and we start a little bit more fast paced. Okay. So we said this is something that we say it's important only to a certain degree. Those factors doesn't matter. Those constants not matter. That we want to use a more scientific or more fancy notation to describe this. This is people talk about the big O notations. Okay, you have something. Oh, this algorithm is ON. This algorithm is ON square, and so on and so forth. So what are these O things? Okay, and this is something that in the next few slides, and we will solve this mystery. So if we have a function fn and another function gn, and this is the simple ones that we want to get to, and we say this function fn is OGN. It's basically, we can call this OGN. This is kind of the official definition of this. And by the first reading, you may seems like a very scared, but it's not that. It's basically saying this: if the n goes up, if the n goes up to a certain size, large, as long as it's larger than n0, and there is a c, the c you can find this constant, and this fn is actually less or equal to this cgn, and then we will call this fn function is OGN. Okay. The gn function usually is one of those 7 functions we talked about earlier. The n squared, n cubic, 2 power of n log n log n, so on and so forth. So we want to kind of bound this, our actual function, by these 7 kind of a standard functions in this O notations. So for example, we have a fn. We have this fn function is called 2n plus 10. And we have our final max is 5n plus 5. They are all the same. We say this function is ON. It's bounded by the linear function of n because what? Because this 2n plus 10, based on this is the 2 plus 10 is this fn function. As long as I can find a c, constant c, and also find the constant n0, and this function is going to be less or equal than the n. And the mathematical way is this: if we set this 2n plus 10 less or equal based on this, c is the c, gn is this function n. So if we solve this function by doing simple math here, as long as we pick c equals to 3 and while n0 equals to 10, we'll have that condition. So look at the chart here is this. This is our original 2n plus 10. This is the solid blue line. And this is the dotted blue line is 3n. And this n itself is going up like this. So you can imagine when everything goes up, when the n becomes larger and larger, And this line, the actual line and this line, only there is a constant factor in between at most. They are actually going to getting closer and closer with a matter of constant factor. So this speed, this growing speed is the most important things we want to grasp. And this is the point of this big O notation. No matter how complex the algorithm it is, we want to see how this O notation bounded to which one, okay? And so like if you have n squared, there's another example for this quadratic function. It's a O(n) square function. So this is, so like this n square function is not O(n) because you cannot find this constant c and n0 to have this condition n squared is going to be less or equal than the Cn plus n0, okay? So there are some examples, like those ones, what is this? What is this? What is this? So simply put, this is O(n), this is O(n) cubic. In all lower terms, this is the highest term, n cubic term. This is n squared, the lower terms. Those things can be ignored. The conclusion is basically this. So you can find the most powerful term in your function, and you call that O something. In a mathematical, we have kind of go over that. How do we define that big O notation? And that's the conclusion is that you want to find the highest order, and then you use the highest order to get your results. So if there is one here, like a 3 log n plus 5, we know this is O log n. But however, if there is something, the particular algorithm executed in the 3 log n plus 5 n, if there's another n here, what would you say if you use the big O notation? Which term is higher? Is it log n? Is n? Great, Alice, thank you. So this is going to be n, okay? So you pick the high order term, you get the one. These are the specific way to get that. And if people want to get to know why it is, and you can certainly to do the math to do that, only by exercising all those details, you would probably remember the results much better, much strong and convincing, and remember them more strongly. So that's the point why you want to do those specific mathematics calculations. Otherwise, if you can remember the results, just remember the results, but not as much as the one if you know why you got the results, okay? And here, this is another way of saying comparing the Fn and the Gn. It doesn't really matter too much. This is the way we have already talked about this. Take out, drop the low order items, drop the constant factors, and that's your results. That's big O notation. Okay, so this is another way of just saying, to summarize that we have how to come up with to get the big O notation. And then you can kind of, and then we just say our find max algorithm is going to, so runs in O(n) time. Okay, this is in big O notation way, fancy way to say how complexity of this find max is. in terms of the time complexity. And there's another space complexity about how much space this algorithm is going to consume. And that's something else. And nowadays, it's not that really important. The time one is the most important one in the RAM model. That basically our storage space is unlimited. You can, Okay, so this is another example here. I was going to go over this to see how this one, but I think we are just short of time. We have 1 minute left. I probably leave this to our next class to talk about this. And this is very interesting if has something to do with the calculation of moving average. And also if people trading stocks, the MACD, the moving average, how it is calculated. So this is applicable to financial analysis. And there is a algorithm, to the prefix average algorithm, that you can go over this by yourself first to see if you have any questions about this. And this is a great exercise to review what we have talked about in this lesson. And then we can come back if to review this on Wednesday and to see how this has been done. Okay, the last few slides, there's a couple of different ways to calculate this average, the prefix average. There are 3 algorithms, and the 3 algorithms takes ON square, and the last one actually is ON. So same results, achieve the same results. Your algorithm does matter. And the one is ON square, and the one is the ON. Why? And that's, you want to write an algorithm that's ON instead of just ON square. Okay? So some kind of, there's a few maths that you want to review to understanding how this basic operations, mathematical functions to do. You can take a look on that. There's another 2 we talk, people always talk about is in terms of the big O. We have, say, the big omega and the big theta. Those are 2 things, if you want to, it's not really, the only thing you want to remember is the big O is the upper bound. So the algorithm will not exceed the big O notation, will not take more than the big O. The omega is, on the other hand, is the lower bound. And basically says your algorithms will execute always larger than this amount. You will wonder why we want this big O, big omega, right? So, and if some algorithms is bounded, is bigger, if it's less than big O, and it's greater than the big omega, and we call it big theta. So theta. So these are the 3 relevant ones. If someone are really interested, you can go over those ones in the books. And if you want me to explain them, I can do this our next session. Give me some feedback on that to see if you want to talk about this. I will go over some of those previous prefix calculations in the previous this just to give you a better understanding, to see if it's necessary. If people think that you are all comprehended on this, then we are ready to move on the next one. Okay, that's about for this class. So same, this is going backwards, so this is upwards. And so this is the last slides of this class. Again, back to my earlier question. anyone would like to have some review on the Python itself, or we just focus on the structures and algorithms? Give me some feedbacks. And you can say yes for the review of Python, or no for the review, and we keep going on the algorithm side and go on to constructing the algorithms and how do we construct algorithms in efficient ways. Okay. I got 2 feedbacks, and just send your feedback in, and then we are done with this class, and you can leave.
Can we see the slide before Wednesday?
Sure. I tried to put up something there. Maybe that's another way to. It depends on if we want to go over the Python itself or not.
So I have one question. For the master theorem, is tied with the big O, isn't it? Is also applicable to omega or theta?
Which algorithm?
Called a master theorem. Essentially, how do we calculate the complexity of the big O, for example?
Master theory?
Theorem, yeah.
Master
Okay.
theorem. I am not. Maybe you send me something more detailed. Ask, give me more links on the master theorems.
Okay.
And
Thank you.
we can talk about this. You can send your question in the Google groups.
Okay.
Yeah, thanks for everyone's participation, and thanks for all those people sending me back the focus, your comments, your inputs, and I have got like most people like to go on to the algorithms, and there are maybe 1/3 of people would like to go over some of the Pythons. So if this is the case, I probably just pick up a few things. I feel that not basic ones. The basic ones, I think everybody probably have a very good understanding of that. And just pick a few interesting topics, a few points, and maybe say a few words about it. And it depends on your homework. Okay, there is a homework, or there's a project. You can try to complete as early as possible to see. I actually would like to see if how you're doing with your project, and then see, so I have understanding of how your knowledge about the Python. Okay, I got someone saying that yeah, you guys have separate the Python class, so I should not focus on anything on the Python itself. Okay, that's great to know. So, and I probably, most likely is I'm going to focusing on more on the data structure side and algorithm side. And this is our first lesson, the first 2 hours. We are all get along with each other and try to adjust our class speed to like fine tuning things and to get into to fit both sides to get everybody a fun and rewarding session, class, quarter, whatever. I'm going to be here for a few minutes, and I think everybody's still here, and I'm going to leave. And if you have any questions, post them in the Google groups, and I'll check periodically. And any questions are welcomed. And I try to, the main point for me to be here is that to help you. And if I can't do this, there's no no meaning of myself being here, and try to take advantage of that to make use of my resource. Okay.
Do we have homework this week?
Yeah, you already, the homework is already in the Google Drive, the folder homework, and also there is a project in the project folder there as well. So check out from there, and it's due next Saturday. Folder links. Folder links is the one, I don't have your email address or things like that. Glenn, maybe, could you please, I think you have already done so, probably. Everyone should have access to the folders, right?
Yes, we received the email from Glenn.
Yeah. So, okay. So if you didn't get the ones, and check with Glenn and to see where the folder link is. I'm just responding some of the questions coming up from the chat window. Okay, I am going to leave and have a wonderful day and see you on Wednesday.
Thank you so much.
Thank you,
Good
Jim.
weekend.
Thank you.
Okay. Talk to you
Bye-bye.
on Wednesday. See you and have fun. And the homework is not that